Welcome to our Senior Design Capstone. We are Team PYECH, sponsored by the National Oceanic and Atmospheric Administration. Our group consists of 8 members who work to complete the optimization and cloud integration of pyEcholab, a Python tool to help analyze the ocean and what is in it. We have Benji, the team lead, Aaron, cloud lead, Tyler, communications lead, Austin, testing lead, David, version control lead, Mitch, requirements lead, Michael, documentation lead, and Ben, the scheduling lead.
So to start this off, pyEcholab is an open source Python package built by NOAA Fisheries, NOAA NCEI, and CRES at CU Boulder for the purpose of reading, processing, writing, and plotting raw sonar data. While the package already functions at a basic level, it does not do so at an acceptable speed. For example, dealing with 150 megabytes of raw data alone can take a minute at the very least, and that amount of data could cover as little as a few minutes. And considering that the expeditions that collect this data can go on for weeks, the package as it currently is does not function fast enough to handle the sheer amount of data that needs to be processed. So that's where our team came in. The general idea was to take the existing package and make it faster. That wasn't our only goal. We also ended up needing to refactor and rework the code to an extent to help not only with efficiency, but also the modularity that would allow our sponsors to further build and improve upon the package once our team was no longer involved. We also reworked and added to the existing documentation for this very reason, as any changes we made would be worthless if the people coming in afterwards were not able to understand our reasoning for the changes we made. A side goal, though not unrelated to making things easier for those that come after, was to reduce dependencies, as the package was already having issues with several packages imported, no longer being updated or even in use. Beyond that, our group was also working with the sponsors to explore the worth in and how reasonable it was to deploy a cloud instance to run the package, which included already creating that instance and testing both the old and new code with whatever we could get working or not. Our sponsors would have an idea of where they could take the package next. And this was what we did for our senior project.
Our project sponsor is NOAA, NCEI, and CIRES, and the main goal of this project was to refactor and optimize software that they had written. The software is open sourced, written in Python, and is named pyEcholab. pyEcholab reads, writes, processes, and plots ocean sonar data, which is used to do things like map ocean geography and study fish population. So why the refactor? Well, pyEcholab needs to handle terabytes of sonar data. This means that it is crucial that the software runs efficiently. Any unnecessary processing within the program can lead to slower execution times, especially when it is looping through terabytes of data. pyEcholab was written by fisheries, acousticians, and data managers at NOAA, so they handed the project to us to study and optimize the code from a computer scientist perspective. As a result, we were able to speed up the runtime, organize the code to make it more readable, write clean documentation, and introduce cloud computing to pyEcholab.
Given the sole goal of increasing speed, there are many ways to go about this. As will be later discussed, changing the entire code base is impossible, so that internal locations that can be improved is the only way to get any desired increases. The most obvious case in this code is reducing the huge number of function calls at every level of processing. It was also apparent that the current code base was highly distributed, which is useful for understanding it, but not great for speed. Beyond the internal mechanisms, the amount of computation can also be changed by moving to cloud-based computing or by parallelizing the functions. After investigating where time was spent in processing files, it became clear there were 2 places to focus. The first was the actual reading in of the NMEA encoded files, and the other was removing background from the data. The background proved to be beyond our skill set and was already fairly close to optimize. However, the reader was rewritten and received a 4-fold increase in speed. The largest increase in speed comes from changing the way the data was stored, from a dictionary of dictionaries to a 3-dimensional array. A tiny amount of speed was also gained by merging distributed functions into single classes, where Python can better optimize. The easiest way to go faster is to throw more computational power at the problem. The two ways to do this are parallelization and cloud computing. Since the process within a single file is both fast and requires sequential work, threading proved to be a slow down rather than a speed gain. Perhaps in other languages there might be a gain here, but not in Python. For cloud computing, converting the code to be able to run in an AWS or Docker instance proved to be incredibly difficult. Through hard work and discussions with the AWS team, a working product was created. The biggest issue for this is dealing with edge cases, such as exactly how data at the edge of each file should be integrated, or dealing with when data is missing, incomplete, or corrupted. The final transition from a single instance to a batch is close on the horizon.
This project doesn't lend itself to live demonstrations, as it is a data processing project and has very little user interaction or real-time output. To demonstrate the progress made, the team took time measurements to gauge performance gains as well as demonstrate the newly added Docker. The team found the biggest performance gains within the rewrite of the raw file reader. Testing output is shown for the old reader, an intermediary iteration of the new reader, and finally, the updated file reader. The current reader allows for either improved iteration of the reader to be used, so that the datagram level reader may be used as it is more reliable if some of the system variables change over the course of the file. The datagram level reader does the processing of converting the raw values to SV format on every datagram, approximately 3,000 times per file. The frequency level reader does the conversion only once per frequency per file. This greatly reduces the processing time by more than 4 times faster, as can be seen in the upper image. The other images show the ease of using the Docker file with the AWS, which will be of great use in the future. The team timed each component of the data processing to show gains and find where bottlenecks in the processing were located. The most significant amount of time is taken during masking, a component that we were unfortunately unable to improve. However, as you can see from the images, masking took approximately 2 minutes 30 seconds from each of the processes, leaving a total of other runtime to a mere 12.9 seconds on the original code and 10.4 seconds on the restructured code. This is an almost 20% gain, which is fairly significant, especially when it is noted that this does not include the improved readers in these times.
For me, the project meant that I would get experience with how a real-world development team would function. Just seeing how we go through the process of dividing tests and conquering code requirements seemed like very good practice for a job. It also seemed like a good opportunity to see how reading and understanding other people's code would go. Turns out that can be quite difficult. This project also presented a good test of our skills that we've learned to this point and of our ability to learn and adapt with the situation. One of the crucial lessons learned is to always provide good documentation so that the people who follow after you can understand what you've written. We learned that breaking into smaller teams can efficiently boost productivity and that communication overall is very important. One tough obstacle that I had to overcome was the creation of a UML diagram. The previous team had around 150 classes in use within the code, and nowhere was there a diagram that showed how everything flowed together. So I set to the task of creating this diagram so that the group could understand how the various classes interacted with one another. Another obstacle that I overcame was learning Docker from scratch so that I could create my own Docker image to be run in the cloud. The cloud, or AWS in this case, was also quite the obstacle to overcome since we had no real experience with it. So overcoming the permissions and understanding what permissions were needed were the most crucial part. Piecing it all together was the final big obstacle. Some of the key strategies I've defined for success are not being afraid to ask for help, starting earlier than later, asking your sponsor for helpful resources, and keeping constant communication with your team. Overall, this project was a good test of our skills, and I thoroughly enjoyed being able to help NOAA advance their project.
At the start of our project, it took us a significant portion of time to read through and understand the codebase we were tasked with improving. There were hundreds of classes, lots of very verbose comments detailing the science behind how the code was working, and it was very hard to know where to start looking. Our solution was to have each person on the team look through the codebase and gain an understanding of it. Given how much time we had for this project, this was an okay approach, but it still took a lot of time, and each person didn't necessarily come away with the same understanding of the code, given how layered it was. This brings to light the importance of documentation, and not just any documentation. The code we had to look through had plenty, but it still didn't help as much as it could have. One of the main takeaways I learned from this project is that concise documentation is better than lots of documentation. Comments should be short and to the point, telling me things about the structure of a file or class, what a variable is used for, or where the workflow starts. A professor once told me not to use comments as code deodorant. When we neared the end of our project, we wanted to learn from this and improve the documentation so that any developer who wanted to work on this repository in the future would have a solid starting point. To do this, we created a wiki. The wiki would serve as one centralized dictionary of documentation. The same amount of information is still available within the repository, but it should now be much more manageable for new developers to be onboarded and for current developers to look up what they need to know.
From the very beginning of our project, one of the principal considerations for our team was scheduling. Though this was, of course, necessitated by the class structure, we knew that setting firm deadlines for ourselves and keeping up to date on what we needed to accomplish would do a great deal to keep our heads above water, regardless of circumstances. While this would be useful in all classes, it was especially fortunate that we were so proactive given the circumstances, sticking closely to the sprint schedule and consistently staying not only up to date, but ahead of what we needed to have done, turned from simple utility to a true blessing once the pandemic broke out. With graduation being canceled, stay-at-home orders being issued, and classes moving to online, many of us found ourselves overwhelmed, stressed, or simply in bad mental states, and the progress we had made on our project prior went a long way in giving us the time and energy to deal with this incredibly unique and disastrous situation, while still permitting us to fulfill the needs of our sponsor. All in all, this fundamentally illustrates the importance of diligence and scheduling, not only for expected timelines and goals, but also for unexpected or dire situations, even those with functionally no parallel in living memory. By staying ahead, we protected both the project and ourselves from previously unimaginable difficulty and strain.